Light rays travel through space in a straight line at approximately 300,000 kilometers per second. As light passes through a transparent medium such as water or glass, its speed is decreased. For glass, it's reduced to 200,000 kilometers per second, and for water, the speed is 225,000 kilometers per second. If the light enters into a medium perpendicular to the surface, it passes straight through, but at a slower speed. However, if the light beam arrives at the medium surface at an angle, not only will its speed be reduced, but it will bend due to a process called refraction. To better visualize this phenomenon, let's look at this diagram. As a beam of light reaches the surface of a medium, the lower portion enters first and is slowed down. However, the upper portion is still traveling at the speed of light until it arrives at the surface and enters. This speed difference at the top and bottom aspects of the light path causes it to pivot, bending toward what is referred to as the normal. This is an imaginary line drawn perpendicularly to the surface of the material. Transparent materials have what is called a refractive index. This is the speed at which light travels in a medium compared to light traveling in a vacuum. For example, typical glass has a refractive index of 1.33. This is calculated by dividing the speed of light in a vacuum, 300,000 kilometers per second, by the speed of light in glass, 225,000 kilometers per second. The refractive index of air is 1.0003. Anytime a light beam travels from a medium with a low index of refraction, like air, to a medium with a higher index of refraction, like glass, the beam of light will bend toward the normal. Likewise, when the beam of light exits a highly refractive medium into a medium with a low index of refraction, the process is reversed. The bottom portion of the beam of light exits first and resumes at the speed of light, with the top portion still at the speed determined by the medium. This causes the beam to pivot away from the normal line. Light is an electromagnetic wave that transports its energy at a speed of 300,000 kilometers per second. This constant speed is how fast light travels in a vacuum and is referred to as the speed of light, or c. When light encounters a medium such as air, water, or glass, it propagates through the substance at a net speed that is less than c. This slowing down of light through transparent objects is a form of energy transport that involves the absorption and re-emission of the light wave energy by the atoms of the substance. Imagine that the electrons in an atom are attached to the nucleus by springs. The elasticity of these imaginary springs will determine how much the atom vibrates when acted upon by an incoming particle of light energy. When light impinges upon the atoms of a material, its energy is absorbed. This absorption of energy causes the electrons within the atoms to undergo subtle temporary vibrations. This transient vibrational action is transmitted from one atom to another until it emerges from the other side of the material at the same light wave frequency and speed. While these vibrations are only short-lived within each atom, overall these actions delay the transmission of the wave energy through the medium. Thus, while a light wave travels at a speed of 300,000 kilometers per second through a vacuum, or the gaps between atoms, the absorption and re-emission process in different materials results in the net speed of the light wave to be less than the speed of light. In water, light travels at about 75% of its speed in a vacuum, or 225,000 kilometers per second. In glass, light travels at 67% of its speed in a vacuum, So the light speed is 300,000 times 0.67, or about 200,000 kilometers per second. Light travels very slowly through a diamond at about 41% of the speed of light, or 125,000 kilometers per second, which is less than half the speed of light in a vacuum.